Okay, here's introduction to Chapter 19, which is magnetic fields. It's actually a two-part topic, which we'll see when we look at the end of topic sections here. We're basically looking at magnetic fields and their effect on each other and effect on electromagnets and electromagnetically charged particles, more of which details later. Okay, so we'll look at accelerators and so on. And then the second part down here is actually about creating electricity, generating electricity in terms of power stations, which we'll then build on, but also the kind of the basic principles behind it, Faraday's and Lenz's law, which is really what it's all based around. Okay, now it's a big practical subject in terms of lots and lots of tiny little practicals to just get a feel for things. So I'll try and film some stuff. We'll see how it goes during COVID, but otherwise it's the little things that we do in class. So just simply sticking magnets to stuff and seeing what sticks to it, what doesn't, what stops it, and things like that. So without that, we're just going to dive in, just give you a bit of background. So section 1 is actually, if I find the sheet, come back. Okay, section 1 is all the background, and what this is really just stuff that you've fiddled with and played with over the years, bringing in terminology to it. So playing with magnets in Key Stage 2 and Key Stage 3, playing with electromagnets, maybe doing an investigation to pick up paper clips, stuff like that. Okay, or pins to have a smaller resolution, pick up on that. So basic ideas is what actually is magnetic fields. Well, the magnetic fields are very similar to electric fields and gravitational fields, except the equations are not as simple. So we're going to cover this in general in the same way, but there hasn't got the maths that the others do. So first things first is we don't have any single mass creating a field or charge creating a field or anything else creating a field like we do have gravity. Okay, so gravity, you can think of it as one object causing the field, and any other mass in that field will then feel a force, experience a force. We don't have this. With magnetic fields, it's all about how both magnetic fields affect each other. Okay, so it makes it more complicated. However, the principles are the same. So, you know, you'll have seen magnetic field lines flowing. You'll have put iron filings onto near magnets, and that will go out and show the invisible field around that. Basic idea is that they are loops. So these are, very importantly, complete loops. If you look at the work, the mathematical work of Robert Maxwell, sorry, not Robert Maxwell, Maxwell the researcher, Scottish scientist, his work on electromagnetism and electromagnetic lights and things that we're still finding out ideas from, so even though it's about 150, 200 years ago now, his work and his equations, often voted the most iconic equations for physics, are based on the principles of electric fields, where field lines flow from one charge to another, so they go from positive to negative. Magnetic fields, they're loops, they're completely loops. Okay, but usually the loop comes from one end of a magnet, one pole of a magnet, could be the side, could be an edge, could be all over, anywhere really, but it will flow out at one point, it will flow round to the other pole and go back in, but it's actually going through and forming a complete loop. Okay, so in principle we're going to say it flows from a north pole to south. Okay, it comes obviously from the north and south pole of the Earth, however they're not actually in the same place as the geographical north pole, the centre of our spin. Okay, the magnetic fields of the Earth move and change, so these aren't fixed, but we still use that terminology. So they come out of the north end and they will flow to the south end, and you can use something that is magnetic to experience that force, for example a compass, and that will line up with field lines. it'll actually flow in that direction pointing to the South Pole. I'll let you think about that. It means that our compasses are actually the wrong way round in the Earth, but it doesn't really matter. So it's the flow. You will need to know the direction. You won't necessarily need to know that it's out of an end or a side or whatever. Field lines, still very similar to electric and magnetic fields, but this is known as not field strength. Okay, so the density of the lines, the closest to the lines, actually has the old-fashioned phrase magnetic, obviously, but flux, and it's this idea. Flux is this idea of flowing in a complete loop. Okay, so that's what we still use it, and it kind of works, but it's actually the magnetic flux lines, but what matters is the strength of it, which is about how close those lines are. So we talk about the flux density, and that is our key concept. It's given or represented in equations by the letter B, capital B. Okay, and it's that's measured in Teslas. It's not the magnetic field strength. That's actually beyond this course. It's used a lot in engineering, and it's measured in Henrys. Okay, so yeah, great name, but we're not going to study it. And it does relate to this, so it does relate to Teslas with one multiplying factor that we'll bring in, and it appears in all magnetic field equations, okay, which is known as permeability. Right, key bit for us is that we can make certain materials magnetic by creating magnetism in them. Now, we actually go a bit deeper, and we now know that it's down to the nuclear spin. It's the quantum spin of nuclei which gives us magnetism in things. So it's not quite what we've got here, so we're not creating it. But we are like inducing electric current. When we make and generate electricity, the electrons are already there. We're just making them move. Okay? So we'll bring that back round to this. It's not quite true like this, but we still use the terminology of creating, inducing that thing. Now, how it does it is that we can use electric currents to create magnetism as well as the other way round. Okay, so we get electricity and magnetism, and they were the two of the first forces that were actually merged together. We realised they're two sides of the same coin. So we're going to talk about electromagnetism. We're going to link that stuff with light, and it does link into the multiplying factor to do with Teslas, but treat them separately. All the questions will be about charge, or it will be about magnets. It won't mix them together. Okay? So we don't really need to use this, but we do need to use the arrows. If we draw magnetic field lines, the thing that matters most is what they're actually doing. So if you get fields clashing, okay, so for example, you've got two magnets. Let's say these sides are our poles, and our field lines are coming out and they're bouncing off each other. Okay, those going to end up not combining. They're actually fighting and forcing each other apart. Okay, so this is what causes them to repel. Okay, excuse me, repel. So this kind of clash sometimes works for some people, doesn't for others. Others, if you try two magnets and you have them so they are attracting, what you'll find is if you put the iron filings near them or other ferromagnetic detectors, what you get is, you get magnetic field lines flowing from one to the other. Okay, and that's because they're coming out of one end and they're going into the other. So that's where the arrows come in. So these might be coming out or we're going in, but they're both doing the same. So let's say these are south poles. We've got our magnetism flowing into those south poles. Okay, as we said up there, so they're coming into the south end from the north. So easiest way for most people is if this idea of merging together works, which causes attraction, or for the sentence, makes magnets attract rather, you might want to think of this, a really powerful little idea, to think of these as like elastic bands. And when you, if you have elastic bands that are like this, it's like they're being stretched, they will pull things together. So it's always trying to shorten these lines. That will work with a lot of our kind of explanations. Don't put it as an explanation, but it'll get your thinking. So will this motor spin this way or that way? It all depends on this idea. So makes everything a little bit easier for most people. Okay, quick heads up. We can make electromagnets because then we can turn them on and off. We can make them stronger and weaker and all the rest. But all these discoveries were, you know, way before the electron was discovered. So we still stick with labeling diagrams with conventional current I. Okay, so just be aware of that. Okay, all of that is our main ideas. The problem is it's three-dimensional. Everything in electromagnetism works perpendicular to electricity. You may recognize the Fleming's left-hand rule that you did at GCSE. Everything's at 90 degrees to each other. That means that drawing diagrams is awkward. Okay, so there's a little bit of convention down here. I'll mention it in the lesson when we do it, but rather than looking at lines side on, often we're trying to look at the ends of them. So there's two symbols that shows the flow of energy. It could be electric current. Here's a current, the end of a wire, and here's the tip of the arrow coming out of the page. So notice that phrasing, that's a really useful way of putting it. So coming towards you, don't say up, because that could be up, or this could be up. So to say out of the page. And if you see crosses, then it's going into the page. It's like the tails of an arrow going in. Okay, so that's really frequent. If they're in a circle, that's the wire, so you're looking at the ends of the wire, but they'll often draw it for a magnetic field. They might draw a grey area, a grey box on a diagram, and they'll just have arrows on it. And because you can't usually see dots, they nearly always have the magnetic field going down into the page. Okay, and sometimes when you're trying to work things out, it might be easier to move your diagram around, for example, on here. So I'm going to introduce this rule. My hand works that way. It's kind of hard to hold it that way. So turn the page. It makes it much easier to line it up with your diagrams. Okay, so don't be afraid of doing that in the exams. Okay, so crucially, a lot of GCSE people do learn two of Fleming's hand rules, and I won't give me joking because they barely fit in the picture. So I could use, and you may have learned, two rules where the hands are at right angles to each other. That's obviously confusing. The fingers and the thumb represents the same thing, so do those two, but those two are obviously pointing in opposite directions. So don't use that. Okay, that just confuses us away from the bit we'll do in the second half of the chapter about Lenz's law. Okay, so the key is we will still use two hands, but we use them for different things. And for most people, thumbs up works really well. Okay, because most people use their right hand for thumbs up. Right? So if you're a right-hander, it's going to be easy. Always use your hand in a grip. So this is called the right hand grip rule. So it's the right hand, not the left, fairly obviously. And the reason is, again, if you do it with your other hand, your thumb is pointing in the opposite direction. So these represent something, but so do the thumbs. But yeah, they're doing the opposite. So right hand is a grip rule. Okay, and that tells us a lot about electromagnets on their own. Okay, doesn't tell us about motors, but this right hand rule works for all things that are just electromagnets, and then we can combine it to go a step beyond. Okay, so for example, the work of Ørsted. Ørsted discovered, allegedly by accident, that electric current, when it flows, creates magnetism around it. He actually did a bit of research on it, played around with it. So what it does is, if you have a wire flowing nice and straight, then if you, with the current going up in this diagram, if you put your hand around the wire in the grip and you point your thumb in the direction of the current, what that shows is that the magnetism is flowing around in this direction. Okay, so it's from left to right on top, but underneath it's from right to left. So it's curling around in perfect circles. So if you just have a single wire or a single conductor, single bar, or a group of wires all next to each other like this, you'll end up with big ripples of magnetism spreading out. Okay, and we can get the direction of it. We don't really have a north and south, so it's really about the direction of the arrows. The direction of it we can get from this right hand grip rule. Okay, so here's my picture here. This ties up with that. It's all about where the thumb goes, so don't need to worry about acronyms for different things like you did with the Fleming's left hand rule. It's just the magnetic field is the curly ones because they're the ones going around. So magnetism goes around. And this, as I said, is very importantly called the, and I'll put the first bit in capitals, the right hand grip rule. Now, what that means for later is when we are doing things like motors and you need this hand and you don't know which one, well, that one's your grip rule. So your right hand is a grip, it's the left hand that we use Fleming's. Okay, so one grip, one left hand rule. So keep that in your head, keep going, thumbs up. Most people are thumbs up on the right hand, very few tend to use their left. So that is correct, stick with it. Okay, now the clever thing about that right hand grip rule is if we go on to the next page, it will also work if we have a coil, or in this case a solenoid, which is just a very long coil. Okay, so when we use the word coil, we tend to mean a flat ring. Okay, and it might have lots and lots of turns in it, so each one of these is a turn rather than calling them coils because that'll get confusing. So on our solenoid here, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. So we've got 10 coils there. 10 turns there. Whereas in a coil, it will be a nice flat circle. Okay, and I'm going to pick that up because they do occasionally get used, but nearly always we use this because it's much more useful. So a long, thin number of turns, sometimes called a long coil, but in the exams it's always a solenoid. All right. So in this one, what we've got here is I've swapped. You'll notice I'm still using my right hand grip rule, but what I've got is my fingers are curling around still, obviously, because that's what they do, but it's actually curling around in the direction of the current. So I've swapped field for current. So it doesn't matter because my thumb still points in the direction of the arrows. So here my fingers are following the arrows of the current, my thumb is following the direction of the magnetic field. Okay, so if I spin that around, that's my B field, that's my flux density, and it's coming out of the north end of the magnet. Okay, and it's going round just like a bar magnet, a permanent bar magnet like used in junior school, and going back in to the south end. Okay, so there's our B going in, coming out the other end. Now, if we link it with, excuse me, I'll turn it upside down so you can see it. If we link it with the diagram on the bottom of the previous page, you'll notice here the field is obviously getting bigger. The area, sorry, the length of that circle, the circumference of it is a lot bigger. The strength, shall we say, the flux density is actually dependent on the radius. So if we double the flux density, if we double our radius, our flux density will halve. It gets a lot weaker. But with this, where each part makes a little ripple, a little circle of magnetic field around every single piece of wire that carries current, so all of that is creating its own magnetic field. What that means is down the middle, we're actually crushing together all those fields and creating a really high density. So down the middle, we got a large flux density with solenoids. These are not much use on their own, almost never used, okay, apart from the definition. If you look it up, the definition of 1 amp of current is based on the idea of single straight wires. But most of the time, for practical use, we're going to end up with one of these solenoids, and what we can do is we can put down the middle something that is going to be easy to magnetize, and that's a really powerful idea, because the electric current on its own doesn't create a strong magnetism in air or in a vacuum. But if we put something that is soft, easy to magnetize, that means if you put something like soft iron, then the electric current creates magnetism and makes the iron magnetic, and the iron is the strong bit of the magnet, okay, creates the high density, the high flux density. The current themselves can be often needs to be quite big, but often doesn't have as big an effect. So it's this, as I say, soft iron, which isn't soft and squidgy, it's soft and easy to magnetize and demagnetize, turn on, turn off, change the strength. That can be a good core that goes down the middle of your coil. That core might multiply it 10,000 times, 20,000 times. You know, this is where we change and research materials to get the best we can. Okay, so other ways of maybe thinking about it, a little bit of playing around here, is that if you're looking from the end, wire goes down on the left, going around, so actually what I've got is a coil that's running a bit like that, so it's down on the left. If you can see the far end, it's going up on the right, so I've got my current going up on my right and it's coming down on my left. Okay, so that's my current there. That, if I put those arrows going around the coil and I join them together, that conveniently gives me the north end of a magnet. Okay, so I can put little arrows on the end of my N, and if they circle in the same direction as the current is, then again, as you can see there, I've got the north end, it's coming out from that end, so it agrees with it. It's quite a nice little way of thinking about it. If you look from the other end, it's going up on the left, so actually same diagram, oops, going down on the right. Okay, so this time it's doing the other way. Again, there's a current. Then what we're ending up with is our magnetism flows in that direction. Sorry, our electric current flows in that direction, correction. And that can conveniently be made into an S. So this is your south pole. Okay, so that might help people, because it's really quite hard to think three-dimensionally if you're not a good visual learner. Okay, so this is maybe a convenient way to think about it. But most of the time, you can work best with the right-hand grip rule. Now, crucial bit, okay? The bits that really matter, and again, these are based on the maths, okay, or I'm going to base it on the maths, but it's the idea from the maths. So the length of the solenoid matters. If you stretch it out, you actually weaken the magnetism down the middle of the bit. We still get the same amount of magnetism, but it's more spaced out. So flux density, the field lines density, is less. So if we squeeze it up, if we make L shorter, then what you'll find is you get a stronger magnetism, stronger magnetic field. So the strongest bit is down the middle. Okay, that's central axis. So all the way along, I should say, along the central axis, we end up with basically B, depending on several factors. Okay, it depends on, obviously, I'll work it backwards. I, so you turn up the current, you're going to get stronger magnetism. There's more energy in, more energy out. That's kind of logical, but they're proportional. So if you double I, you'll double the flux density. It depends on how many coils you've got. So I'm going to put N there. And N is the total number of coils. If you have 2 coils, then effectively you've got twice the current flowing along next to each other. So doubling N will also double the flux density. However, if you spread them out over a certain length, as I say, makes a difference. So if you squash this up to half the length, again, you're squashing the field lines to twice the density. So again, flux density depends on those. So all of those are logical variables, yeah. The only other variable that matters is this thing called permittivity. So this is just the exact equivalent of the permittivity for electric fields. The permeability, confusing I know, permittivity and permeability of the electric and magnetic fields goes together to make the permeability for electromagnetic rays. So it kind of links in with light, and this is, you know, obviously took a bit of a step, but Maxwell's equations brought those all together. This is on the data book. I shall put it in here. So it's, again, like, just put it there, like the epsilon. Okay, so I'm going to say equivalent to epsilon. Free space still, so a vacuum. This is perfect. But the permeability is the ability to hold in place the magnetic field. Just like that held a strong electric field. Okay, so capacitors, big value, helps. So that permeability of the material, of the core. Okay, so a key phrase there, the core is what goes down the middle. If it's just air, then it's pretty rubbish. Okay, the data book value, 4 pi times 10 to the minus 7, so it's pretty small. Not as small as that, but it's still pretty small. Okay, so what you want is to actually multiply that by something that has a relative effect, relative value of, I don't know, 1,000, 10,000, 100,000 maybe. Okay, so what we do is we will not need that, but what I'm just going to show you is that if we look at the equations for electric current flowing through conductors, but in different shape conductors, fairly obviously we end up with very similar factors. So in a flat, okay, now I should just point out it's not in the spec, the equations aren't in the data book, but the ideas are really important for you to use in definitions and descriptions, sorry, not definitions. So when you're describing something, that's really important. That B is always going to be featuring those. Okay, it doesn't matter on the shape of the coil. I'll just leave a little space because it kind of works on the order. You've always got these same factors. Okay, the bit that changes is the variable. So this one is over for a flat coil. Okay, is 2 times the radius. Okay. If it's a flat wire, it's the circles around the wire and it's the size of that ripple, the circumference, so it's 2 pi r. Okay, so those are multiplying factors. And this one literally just depends on the length. Okay, so it doesn't matter as long as the length is bigger than the width. Okay, so that's our definition as such of a solenoid. It's longer than it is wide. Then it doesn't matter. You're always going to get that same factor, so it's just the length. But we can multiply them up. It's very simply, if we have several coils, okay, if we've got several coils, if we have several single wires next to each other, we'd still have that same number. So you can multiply it up. The factors are the same in every single part. Now, the way I tend to remember this is different. This may appeal to you if you're trying to memorize stuff. I use a little n, little n is used for coils, number of turns per meter. Okay, so it's a simple way of doing it. It's just the same thing. Number of coils, number of turns around the core, and the length of it. Okay, so those are the key basic ideas. These variables are important. The material features everywhere, okay, and some materials are better than others, but the key word, okay, is the ideal. So ideal core is easy to magnetize and demagnetize. So for example, if you had an electric bell, or you're walking through a scrap heap on your way to a party dressed as a knight, and you walk past the electromagnet, you don't want it to stay on. You know, once you turn the current off, you want your magnetism to stop. And if this was a hard material, it would stay magnetic. We don't want that. Okay, so ideal core, soft, that is a technical word, so soft iron, which, as I say, is not like putty, it's just soft, the opposite of hard. Bit of a strange word. Okay, so that's the first section. The second section is then actually about uses and things like that. So those 2 pages there, that's all the background stuff that hopefully you saw. I should just add on, because I've put my arrow, so coming out the north end into the south. There we go. Etc. Just little tips, little ideas, things to use, and hopefully clarify. But key things, going back to this, is it's all down to thinking about what can be permanent and what can be an electromagnet, okay, and trying to talk about flux density. So when we talk about flux, that's basically lines, whereas that's the bit that matters, how close the lines are. It will not matter, that difference, it will not matter at this point, but it does when we talk about inducing, creating electric current. Okay, so the second half of the chapter, that's really important. The first half, yeah, there's field lines, and the closer they are together, the stronger the field, the higher the density. Okay, and those are the language we need to use. So, nice and simple, big ideas, really useful.